So yesterday we talked all about physical properties. We said physical properties are things that can be measured or observed without changing matter, where chemical properties really describe the making or breaking of bonds or the interaction of matter. So what we're going to do today is talk a lot about measurement. And we talked about it a little bit yesterday, but we're going to talk about it in a lot more detail. So measurement of matter. There was a really big problem in, I believe, the 1700s, where every country had a kind of different system of measuring things. And so everyone got together and they decided we need to standardize this. We shouldn't have a different length measurement in England versus China or somewhere like that. So they tried to get together as many countries as possible, and they created an institute. And I'll write it out, but you don't have to if you don't want to. So it's scientists use the Système International des Unités. I don't know if I'm pronouncing that right. It's French. Typically we call these SI units. So it's the international system that's used by all of the major countries in the United States, with the exception of us and where else? Who remembers? Burma and Libya, right? We should get our stuff together and get on board with SI units, but we're a little slow. So let's do a list of physical properties. And then we'll have the SI unit. And then we'll have the symbol that's used to represent that unit. All right, first one, we'll do length. Pretty easy. Does anybody know what the SI unit is for length? It's not yards. It's not feet. Meters, right? So if you've ever been up to Canada, they measure everything in kilometers and meters. So we'll put in meter. Some countries, too, will spell this R-E instead of E-R. You might see that with theater, too. Americans typically do M-E-T-E-R. The symbol for this is just a lowercase m. Make sure you do lowercase for meter. You don't want to do uppercase because that means something entirely different. Next one we have is mass. What was the SI unit for mass? Kilogram? Yep. And I'm going to put a little asterisk up here because this has a prefix in front of it, kilo, right? So it's 1,000 grams. This is the SI unit, but chemists oftentimes just work in grams too. What's the symbol for kilograms? kg. Again, all lowercase. All right, next one we've got volume. SI unit for volume is what? Yeah, so we can do milliliters, cubic centimeters. Oftentimes, you'll just see liters. Again, chemists typically use milliliters instead of liters, but if you take a physics course, liters is more common. In this case, capitalization matters. You want to use a big L, not a little l. So uppercase L. Next one, we've got temperature. Temperature is often measured in Celsius. However, the true SI unit is actually something called Kelvin. And we show this with an uppercase K. Does anybody know what the difference is between Celsius and Kelvin? What do you think? Yeah, so Kelvin is a system for measuring things that go down all the way to absolute zero. The problem with Celsius is we can have temperatures below 0 degrees Celsius, and so it's not a very good unit for temperature. Kelvin's a lot better because it starts at 0, and there's actually an absolute hot temperature too. And if you're interested, I can talk to you more about that. Okay, so we've got length, mass, volume, temperature. Next one is time. Luckily, we follow this one. It's just seconds. The symbol is just lowercase s, not uppercase.
Next one is common in physics, but not as common in chemistry. It's current, so electric current. Does anybody know how we measure that? Amps. Yeah, it's confusing. So volt is potential, amps is current. So a lot of times people confuse those two. And we have an uppercase A. The way I remember the difference between volts and current is I imagine a waterfall, right? A waterfall, you can imagine the current going over the waterfall is the amount of water going over the waterfall. Where voltage is just simply how tall the waterfall is. They're completely different from one another and independent. Does that make sense? Okay, and then the next one, we've got luminous intensity. This is typically how bright something is. And this is measured in candela, which is abbreviated CD. This is pretty common now for studying solar panels or how bright a molecule is. All right. And then last but not least, we've got our most important one for chemists. And this is for measuring the amount of something. It's our way of counting. Does anybody know how chemists count, what our unit is? It's a little animal. Mole, right? So some of you have heard about moles. We have mole day. And then the abbreviation for this is just MOL. And we're going to spend a lot of time talking about moles later on. But let's make a little note, too, for those asterisks. Is that chemists often use milliliters, so little m, capital L, or centimeters cubed, instead of the liters that are shown. And chemists often use just the base of grams. So we'll make a little note of that. They're interchangeable. Does that make sense? All right. One problem we deal with as scientists is we are measuring things that are oftentimes super duper tiny or super duper big. So let's talk about using prefixes to get around that. So scientists often measure large or small things. Okay, so here's a good example. The mass of the Earth. Okay, the mass of the Earth is 5970000. I have to count. 00000000000. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. It's this many grams, right? Pretty tough thing to measure. So nobody wants to draw that many zeros. It's a waste of time. How can we fix this? We can move it, right? So we need to come up with some sort of way of moving the decimal point, which is back here, to a more convenient location. So what I'm going to do is I'm going to take this decimal point that comes at the very end, and I'm just going to move it all the way up here. So then the question is, how many places did we move it? What do you guys think? Was it 27? Okay, so 27. So a much easier way of describing this giant mass is to say, all right, we moved it. It's now 5.97 times 10 to the 27th. So we're using exponentials now to describe this. And we can still describe this as grams.
it's a lot easier to write things out this way. It's basically saying we moved our decimal point 27 spaces. Yep?
Are we allowed to shorten the exponential to just e, or would you rather us do it in full exponential form?
That's a good question. So a lot of you guys are used to calculators that will spit out the answer with e to some power. Try to do 10 raised to the power. Most scientists show it that way. E is more of an artifact of calculators. Yeah. So this is true scientific notation. All right, let's do the same thing with another weird example. And then I want you guys to help me write this in scientific notation. This is the mass of hydrogen, specifically one hydrogen atom. Okay, so this is 0.000000000000000. Let me double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 zeros. 4, 5, 6, 7, 8, 9, 18, 19, 20, 21, 22, 23, and then 1, 6, 7. So now what we need to do is we need to move that decimal point to a more convenient location. Where do you guys think we should move it? To the right. After what number? Yeah, probably after the 1. So I'm going to take this. I'm going to move it all the way over there. And then the question is, how many places did we move it? 24. So we moved that decimal point 24 places over. Okay? So if we write this out, it's going to be 1.67 times 10 to the what power? Negative 24. So if you're moving it right, you have to make it a negative number. So the mass of one hydrogen atom in scientific notation is 1.67 times 10 to the negative 24th grams. It's an incredibly small number. Are there any questions with scientific notation? Oftentimes you'll see these written out as a power of 10. However, we can use prefixes to get around using these base 10 units. Yep?
How big is the mass of the Earth?
That's an excellent question. That's way outside of the scope of this course, but if you want to talk about it, we can talk about it later. There's a cool book by Bill Bryson. I'm trying to remember the name of it, but I think he actually talks about it in that book. So if you're interested in some weird reading, Bill Bryson's an excellent author. All right, so let's use prefixes instead of powers of 10. Actually, I'll say instead of base 10. Okay. So my favorite example to use is Batman. We'll do the mass of Batman. I'm not quite sure what the mass of Batman actually is, but I'm guessing he's a pretty big guy. He might be about 95,000 grams. Right? How could we describe his mass in SI notation, meaning base 10 notation? What do you guys think? Yeah, 9.5 times 10 to the 3 or the 4? So let's take a look at this, right? Our decimal point, if we're moving it over here, it went 1, 2, 3, 4 spaces over. So it'd actually be 9.5 times 10 to the 4th grams, right? And you can double check that using your calculator too if you ever feel uncomfortable and you're like, wait, did I do this right? Just type in 9.5 times 10 to the 4th and see if you can go in the reverse direction. All right, let's do it with prefixes. What's the prefix we oftentimes use for mass? Does anybody remember? Kilo, right? So the SI unit was kilo. Kilo is 1,000 grams. So if we look at this, how many kilograms do you think Batman is? 95, right? So 95 kilograms with the little k. And really all this means is it's 10 to the third, right? Or 1,000 is another way of thinking about it. So oftentimes we use these prefixes to describe the base 10 units as well. So did you guys all get a chance to grab the handouts up front? If you haven't, feel free to run up and grab one really quick. And we're going to talk about that sheet. So if you had a chance to go through your textbook has a whole bunch of prefixes. A lot of them, I'll be perfectly honest, aren't commonly used, so I'm not going to force you guys to memorize them. This is the condensed list of prefixes you do need to memorize for this course, or for most science courses. The first one on the prefix list is nano. So oftentimes you've heard about nanotechnology. Nano is something that's incredibly small, right? So the power for nano is 10 to the negative ninth. Micro is also another really small unit. So microprocessor, you always think of something small. That's 10 to the negative 6. Milli is 10 to the negative third. So maybe you've heard of millimeter. Millimeter is smaller than a meter. And then centimeter, or centi, is still smaller than a meter. So all of these top four are fractions, meaning they're smaller than the base unit. So smaller than base. However, as soon as we switch over to kilo, we know that kilo is a multiplier. It's bigger than the base. Really, these are the only ones I want you to know. Nano, micro, milli, centi, and kilo. Oftentimes, students will say, what's a good strategy for memorizing these? I oftentimes, when I'm trying to memorize things, I just get some index cards. I write down the definition, I put it next to my bed, and then every night before bed I flip through it a few times. Before you know it, in 3-4 days you've got them down pat. So I know it takes a little bit of work, but I do want you to remember the symbols for all of these as well. So nano is N, micro has this funky looking U shape, so it's got a tail on the front. Milli is just lowercase m, centi C, and kilo is lowercase k. And you should also remember that kilo is 10 to the third, centi is 10 to the negative 2, milli is 10 to the negative 3, micro is 10 to the negative 6, and nano is 10 to the negative 9. Takes a little bit of work, but before you know it, you'll have it in no time. Are there any questions with this? Chemists once in a while use some kind of non-SI units. One of the really common ones that chemists will use is this one down here, an Angstrom. It's really, really similar to a nanometer. However, it's actually a little bit smaller than a nanometer. So a nanometer is 10 to the negative 9th, and Angstrom's 10 to the negative 10th. The reason chemists use this is it's really convenient for measuring the distance between two different atoms, even more convenient than nano. So you might see this on occasion as well. There's also unit relationships here. So if you are trying to do unit conversions, which we'll do a lot of later, you can use these unit conversions as well. And then at the very, very bottom, this is a handy-dandy table for converting between American units and SI units. So for example, if you're traveling up to Canada, you might want to know how to convert from kilometers to miles, and you could use something like this to convert really easily. A lot of people ask me too, do I need to memorize these? Absolutely not. I will not force you to memorize these. However, I will give them to you on an exam if needed, and you can use your calculator to solve a conversion that way. Make sense? All right. So now what we're going to do is use these prefixes. And I'll give you guys some problems to work on. So the first one I want you to do is to replace the power of 10 with a prefix from the table, so not any of the prefixes that are not on the table. Oh. So replace the power of 10 with a prefix. All right, the first one is 8.01 times 10 to the negative 6, and we'll do grams. Next one, I'll do 1.05 times 10 to the negative 3 meters, and then last but not least, we'll do 7.9 times 10 to the negative 3 liters. So try to use a prefix and then check with your neighbor and see if you've got it. See a show of thumbs. If you feel like you've got this down, give me a thumbs up. If you're kind of hesitant, you can do a side, and if you have no idea what's going on, you can give me a thumbs down. Some waving thumbs. Check with your neighbor and see if your neighbor can explain it to you.
They just want to replace the numbers with the actual word.
Yep, exactly. Don't be afraid to argue with your neighbor, too. Some of the best science occurs when you argue. Let's do the first one together. If we look at our prefix chart, what is 10 to the negative 6? What's a prefix we can use? Micro, right? All right, so if we rewrite this, we could say this is 8.01 micrograms, right? So that's a lot easier than writing 10 to the negative 6. Let's do the next one, too. What's 10 to the negative 3 on that table? Milli. So this would be 1.05 millimeters, so mm. What about the last one? Milli. So we could say this will be what unit? 7.9 milliliters. So M in lowercase and then capital L for liters. Does that make sense? Let's do the opposite now. So replace the prefix with power of 10, or scientific notation. All right, the first one, we've got 45 milligrams, got 125 nanoseconds, and 10.7 microliters. So same thing, check with your neighbor if you think you got it and see if you guys are coming up with the same answers. Yep.
Do we have to keep the number in front of the times 10 to the whatever power between 1 and 10?
Sorry, say that again?
The number that comes in front of the times 10 to the whatever power, do we have to keep it between 1 and 10?
Yes, ideally. So let's do one as practice, I guess. That's an excellent question. So first thing is, what does the little m stand for? 10 to the negative what? Close. Negative 3, right? So m is 10 to the negative 3. Oop. Okay, so if I do this, I could say, you know what? This is 45 times 10 to the negative 3 grams. However, chemists and scientists in general like to really simplify things as much as possible. And remind me of your name again? Max had a good point. He said normally this first number here should be a number that's between 1 and 10, right? So how can we fix this? How can we turn this into power of 10 where it's not 45, it's a number between 1 and 10?
4.1.
Yeah, exactly. So let's take this decimal point that we know exists after this 5, and we'll move it one spot over. Okay, so it's going to be 4.5 times 10 to the what? Would it be negative 4 or negative 2? Think about it this way. If you're going to the left, you're adding numbers. If you're going to the right, you're going in the negative direction. So are we going more negative or more positive? More positive, right? Because we're going to that left-hand side. So in this case, we want to change this from 10 to the negative 3 to 10 to the negative 2 grams. So this would be the most appropriate base 10 unit. Does that make sense?
Can you say it one more time?
Yeah, so when you move that decimal point to the left, you're essentially adding a number to the power, right? So in this case, negative 3 plus 1 is negative 2. When you're going the other way, you want to subtract numbers from that exponential.
Then would it be considered centigrams or something? So it's -2.
Yeah, that's a good question. So there would be different ways of describing this with prefixes. However, if you're going to base 10, you typically want that first number to be between 1 and 10. Yeah, with prefixes, you can choose any prefix you want. Yep. So let's do the next one, and then check the next one with your partner and try to do the same strategy.
Is that supposed to be N?
The which one?
Is that 125 N or
N.
N?
Yeah, sorry.
Oh, that's just an N?
Yep. So nanoseconds. I feel like the longer I was in school, the worse my handwriting got. If you guys can't read something I'm writing, let me know. Otherwise, I'm just going to steamroll right past it. And then let's see thumbs. If you think you got the last two, give me a thumbs up. If you're a little uncertain, you can do sideways thumbs. If you have no idea what's going on, you can give me a thumbs down. All right, looks like we've got mostly thumbs up. So nano is what? 10 to the negative 9. Okay, so if we piecemeal this, we could say this is 125 times 10 to the negative 9 seconds. However, we know that typically we want to move this decimal point further over. So we're moving it 2 places to the left. Does that mean we're going to have 10 to the negative 11th or 10 to the negative 7th? 7. Okay. So this would be 1.25 times 10 to the negative 7 seconds. All right, and then last but not least, we've got micro. Is it 10 to the negative 3? Negative 6. Okay, so this would be 10.7 times 10 to the negative 6 liters. Again, we want to move this decimal point one spot over. So would it be 10 to the negative 7 or 10 to the negative 5? Negative 5. And there we go. So some useful tricks for converting between prefixes and power of 10. Oftentimes, too, I like being able to estimate volumes or estimate distances, things like that, without having to calculate it entirely. So I'm going to, throughout the term, give you guys some useful tricks for estimation. All right, the first one is 1 liter is the volume of an Nalgene. That was something I mentioned yesterday. Other people remember this as saying, well, obviously, if you go and buy a soda from the store, it usually comes in those big 2-liter bottles. A liter is half of that. That's another simple way of remembering it. 1 meter. What's a trick for remembering the length of 1 meter? It's about a yard. If you've ever done swimming, is anybody here a swimmer? So have you been in a meter pool? Is a meter longer or shorter than a yard?
Longer.
A little bit longer. It's super frustrating if you're a swimmer because you get used to your time in yards. You go in a meter pool and you're like, wow, I feel really slow. So 1 meter is about a yard. It's a little bit longer though. All right, 1 kilogram is the mass of a full Nalgene. So if you fill up your Nalgene bottle with water and kind of feel the heft of it, that's about a kilogram. And then 1 gram is about the weight of a paper clip, or the mass of a paper clip, depending on the size of your paper clip. So you can use these if you're trying to ballpark something. Yep.
What is a Nalgene bottle?
Thank you.
Oh yeah. You guys haven't seen it? Oh my goodness. You guys, I guess I come from a slightly different time. So if you've ever been backpacking, they're those polycarbonate bottles. Do you mind holding up yours in the back? They look like that. They're really common for backpacking or just carrying around water. They're usually about 1 liter. That's kind of the standard unit, or 32 ounces. Okay, so let's talk about measuring things in the lab where we don't want to just ballpark it. We actually want to come up with a definite number. And in order to do this, I want you guys to grab this worksheet. So the first thing you should do is determine what unit the hash mark represents. And then estimate 1 unit past that. So for example, with number 1, what are our units for the hash marks? Is it the ones place, tens place? What do you guys think? I'd say each hash mark that you see is a ones digit, right? So if we go through, we'd say this is 10, 11, 12, 13, 14, 15, and so on. You don't have to have a number at each of the hash marks, but you want to know which unit the hash marks are representing, right? So the hash marks are the ones place, which means we need to estimate 1 digit past the ones place. So we need to estimate to the tenths place. So if we're looking at this first one, what do you guys think we should measure this as? 15.9, 15.8. Yeah, the last digit's an estimate, so it doesn't have to be precise. So I'll just go ahead and I'll say 15.8 centimeters. It's really, really important to include units anytime you're measuring something. Otherwise, it's just a random number. Why wouldn't I say 15.8999999? Yeah, we don't have the tools to measure to the 0.99999 place, right? We can estimate 1 digit further, but we don't want to estimate any further than that, or else we're just really guessing at that point. All right, let's do the same thing with the next one. So number 2, there are some smaller hash marks in there, and I want you to check with your neighbor and see if you guys come up with really close numbers. Does anybody want to help with number 2? Not everybody all at once. Anybody? What do you think?
I said about 15.87.
15.87, sure. So in this case, can you guys see how we've got a tenths place hash mark? That means we need to estimate 1 digit past the tenths place. So in this case, it would be 15.87 centimeters. I think that's great. So if we look at this, because we've got the tenths place hash mark, we need to now estimate to the hundredths place. Oh yeah, the last digit, because it's an estimate, will be variable from scientist to scientist. You want to do your best job, but it's not going to be perfect. Okay, let's go through and do 3, 4, 5, 6, and 7 with your partner or the person next to you and see if you guys are coming up with similar answers, and then we'll check as a class. The most important thing to check with your partner is that you have the same number of digits in your measurement, right? So if you've got it at the hundredths place, make sure your partner does too. Or if you've got it at the tenths place, make sure your partner does too. And then if you agree with your partner, give me a thumbs up. Handful of thumbs. All right, so let's look at number 3, 4, and 5. They're really similar. They all have the same units, right? If we look at the hash marks for 3, 4, and 5, the hash marks are at the tenths place, right? So we need to estimate all the way to the hundredths place. For number 3, does anybody want to share their answer? What do you think? 15.3. 15.3. So that would be all the way to the tenths place. Can we estimate 1 digit further? 15.31? Definitely. We want to make sure that we've got it all the way to the hundredths place. We want to estimate that 1 unit further. That looks great. What about 4? Does anybody want to help me with that? It looks like it's right at 15.5, but should I list it as 15.5 or 15.50? 0.50, right? You want to estimate to the hundredths place even if it looks like it's dead on that hash mark. So this would be 15.50. 0 centimeters. We still want to estimate that.
What about 15.05? Would that be
15.05. 15.05, if we look at it, would be closer down here. Can you see how this is smack in between 15 and 16? So it's at 15 and a half, but we want to estimate one digit beyond that. Yeah. All right, number 5. What would we say for number 5? 16 point maybe 00 again. It looks to me like it's right at the hash mark. All right, next one, number 6. Looks like it's between 12 and 13. We've got hash marks at the tenths place, which again means we want to estimate to the hundredths place. So it looks to me like it's about 1, 2, 3, a little bit past 3. So it's going to be 12.3 what? 12.32? Sure. 12.32 centimeters. It makes people feel really uncomfortable at first to estimate that last digit, but it's important that you include that last digit. If you don't, that means that the digit before it is your estimated digit, and that's simply not true. We know for a fact that that measurement is above 12.3. All right, number 7. Looks like, again, we've got it at the hash marks at the tenths place, so we want to estimate to the hundredths place. What would this be? I'd say it's 1, 2, 3, 4. Do you think it's above the 4 or below the 4 or right at the 4? Okay, 9.39, something like that. If you put 9.40, that's close enough, right? So the most important thing is just having the correct number of digits. All right, now we go to 8 and 9. These are measurements of temperature. What do you guys think about for number 8? What do the hash marks represent? The ones, tenths, hundredths place? The ones. So we want to estimate to the tenths place. For number 8, what do you guys think it is? Yeah, it's definitely past the 21, so I'd say maybe 21.8, 21.9. And oftentimes people will write degrees Celsius like that. All right, what about number 9? 36. Is that it? 0.0. You want to estimate one more. So 36.0 degrees Celsius. All right. Number 10 and 11 are the oddball ones. I'm not sure if you guys have ever noticed this, but if you pour water into a really narrow container, the water will start to curve a little, kind of like it's shown here. You guys will see this in lab when you're working with graduated cylinders. It tends to smile a bit. This has a really fancy name. Does anybody know what it's called? Meniscus, right? And the reason it does this is that the glass actually sticks to the glassware pretty tightly, and it doesn't want to form a flat layer. It would rather hug the glassware a little bit. So when we're measuring this, it gets a little tricky. In order to measure the volume correctly, scientists have said, you know what? Measure the bottom of your meniscus. So if we look at this, the bottom of the meniscus would be this blue dot right here. Don't measure up at the curve of the meniscus. That is really hard to do. We want to measure the very bottom. All right, so let's do number 10. What are the hash mark units? So we're between 5 and 4. Yeah, they're the tenths place, so maybe we can estimate to the hundredths place. So what do you guys think the volume is here? If we go up, I'd say it's definitely above 4.1, above 4.2. Is it above 4.3 or below? A little bit below, I would say. So 4.29 maybe? And we have milliliters. All right, what about number 11? What do the hash marks represent now? The ones place, right? So we want to estimate past the ones place to the tenths place. So what would we say this would be? 30.0. Something like that. The key is this last unit on here basically tells everybody else you were estimating that, nothing else. It doesn't mean it's that accurate. It means it's your best estimate. In lab this week for the pennies experiment, you'll also be working with digital scales. Can you estimate any digits beyond what you see on the digital scale? No. Just write down what's on the digital scale. That's good enough. But if you are using something like a tape measure, you want to estimate 1 digit further beyond the unit that you see, and we'll talk about that more in lab tomorrow. All right, I think that's where we'll end today. Remember, tomorrow we're going to be meeting across the hall, and it's a 2-hour lab period, and it will likely take the entire lab period.